Thank you for the introduction. And I will present you the paper entitled Results of Measurements Campaign for Characterization of AIS Transmitters. After a short introduction, I will give you the background needed for this presentation. And I will introduce the measurement campaign and then results about the physical layer, baseband parameters, and AIS protocol will be shown. As it has already been said in the previous presentation, automatic identification system is a maritime communication system. It's mandatory on big chips. In this case, AIS transmitters are called Class A equipment. On other chips, this system is based on voluntary carriage. And in this case, AIS transmitters are called Class B equipment. Nowadays, AIS is based on the VHF terrestrial communication, and it suffers from a limitation in its range of coverage. So there's a will to extend AIS in space, thanks to LEO satellites, but it causes a lot of messages collisions that makes information difficult to decode. So the subject of this presentation is a measurement campaign of terrestrial AIS messages. The goal of this campaign was to better understand the needs of space-based AIS thanks to a characterization of AIS transmitters and transmitted signals in order to help us to design and improve algorithms used at the receiver, such as demodulator or successive interference cancellation or AIS burst detection. This campaign has been organized, funded, and realized by the CNES, the French Space Agency, and the collected data has been analyzed by the M3 System company. AIS is based on the SO-TDMA protocol. The frame of SO-TDMA is a 1-minute frame divided in 2,250 time slots. Each time slot has a length of 26.7 milliseconds. And we have two frequency channels, AIS1 at 161.975 MHz and AIS2 at 162.25 MHz. Each channel has a bandwidth of 25 kHz. The data transfer is based on HDLC protocol. Here is the general message structure of AIS. So there's ramp-up portions of 8 bits for power increase, then the training sequence of 24 bits that consists in an alternation of logical 0 and logical 1 for synchronization. Then the useful data and the CRC are between a start flag and an end flag of 8 bits. And finally, the buffer is composed of 24 bits for jitter, bit stuffing, or power decrease. The used coding is the NRZI coding. So we have a transition in the waveform if the transmitted bit is a logical 0, and no transition if the transmitted bit is a logical 1. The bit stuffing is used to avoid confusing a sequence of bits with a start flag or an end flag. So in the useful data, if we have 5 consecutive logical 1, logical 0 is added. AIS signal is uses GMSK modulation. That is a particular MSK modulation with a Gaussian shaping filter. The phase is modulated in a continuous way, and the equation of the phase is given here. One of the main parameters is the modulation index, that is equal to 0.5 in the MSK modulation. It ensures that the frequency difference between the logical 1 and the logical 0 states is equal to half the data rate. For GMSK modulation, a pre-Gaussian shaping filter is added. The transfer function of this filter is given here. B is the filter bandwidth, and defining T as the bit period, we have the BT product, that is another main parameter of the modulation. For IAS should be about 0.4. A lower BT produces a narrower bandwidth, but also a longer spread of the pulse over time, which increases intercept-band interference. The measurement campaign took place in the Western Rail in northwest of France during a week in October 2011. This rail is a mandatory lane to go to the channel from the Atlantic Ocean. There's about 150 boats each day, so coming from every part of the world, so it's assumed to be a representative set. Two locations for two receiver antenna were selected on the Western Island. The first one is the Tour du Stif. The picture of the tower is given here. That is a maritime control tower. Here the altitude of the receiver antenna was about 100 meters. And the second location is the Phare du Crash, where the altitude of the receiver antenna was about 10 meters. During this week, several acquisitions have been done. Length of these acquisitions is between 10 seconds and 4 hours. Then received signals are treated thanks to a software chain that contains AIS burst detection, demodulation thanks to a non-coherent robust demodulator, CRC checking, message interpretation, and frequency and modulation parameter estimation. Here is given an example of the detected chips on one acquisition. More than 2 million AIS bursts have been detected in the received signal, but in the Phare du Crash, 80% of this AIS bursts had correct CRC, and in the Tour du Stif, only 42%. This is a lower percentage due to the fact that in this tower there was a lot of interference. But finally, more than 1 million AIS bursts with a correct CRC have been analyzed. So first, the modulation parameters. Knowing the values and the dispersion of the modulation index and the BT product is important to define this parameter in the demodulation algorithms. So we estimated these parameters thanks to the maximum likelihood estimations on all the signal lengths. Here are given histograms of estimated modulation index for both measurement sites and histograms of estimated BT product for both measurement sites. About 80% of the estimated modulation index are between 0.49 and 0.51. And about 90% of the estimated BT product are equal to 0.4. So in the demodulation step, the modulation index can be set to 0.5 and the BT product can be set to 0.4. Each AIS signals has a carrier frequency shift due to the transmitter local oscillator drifts. According to the ITU recommendations, this carrier frequency shift should be between minus 500 Hz and plus 500 Hz. So we estimated this carrier frequency shift thanks again to the maximum likelihood estimation on all the signal lengths. Here are the histograms of estimated carrier frequency shift for both measurement sites and the histograms of this estimated carrier frequency shifts for Class A emitters and Class B emitters. We can see that some estimations are lower than minus 500 Hz or greater than plus 500 Hz, and it appears only for Class A transmitters. It could be caused by low quality transmitters, and the conclusion is that the carrier frequency shift can be greater than expected, and it's important to know, in particular for the detection of AIS burst. There was some interrogation of for the power ramp up and power ramp down portions. The question was which is the sequence of bits during these portions. This is a crucial information to reconstruct the signals, for example, for interference cancellations algorithm. So the first thing the first questions was what is the real length of the power ramp up and power ramp down portions. It's theoretically 8 bits, but some of these bits are in the noise. So we computed the length of these two portions. The average of the length of the power ramp up is about 4 bits, and for the power ramp down portion, it's about 2.5 bits. So the analysis of power ramp up is feasible. 4 bits is enough. It's more difficult for power ramp down, so we will focus only on the power ramp up portions. So the next question is, what is the bit patterns of the ramp up portion? To try to determine that, we observed the instantaneous phase. Here we have two representative examples. The first transmitter with 7 received messages and another with 6 received messages. For these both transmitters, phase changes are identical for every received signal. In the first example, during the power ramp-up portions, we have oscillations. That means an alternation of logical 1 and logical 0. And so before NRZI coding, it's a sequence of 0. In the second example, we have an ascending slope that corresponds to a sequence of 1, logical 1. We computed the last demodulated bits for every signals we received. And for 80% of the received messages, the 4 last demodulated bits of the ramp-up portions are identical. So we assumed that in the power ramp-up portions, the sequence of bits is a sequence of the same bits. So the next point is the bit stuffing. According to ITU recommendations, the majority of the combinations of bits needs less than 3 bits for bit stuffing. So we compute the average number of bits used for bit stuffing, and is about 2.25 for both measurement sites. So this result is consistent with the statistics study of the ITU recommendations. But the maximum number of bits used for bit stuffing we found was of 10. So knowing that in the buffer only 4 bits are reserved for bit stuffing, the number of bit stuffing could be greater than expected. Then the initialization bit of NRZI coder. NRZI coding is a differential coding, so it needs an initialization bit. We compute the percentage of these bits in each case, logical 0 or logical 1, and you can see that logical 1, bit 1 is used more often. It's clearly not random, and we found no explanation yet for this imbalance. We also wanted to know which type of messages we received during this measurement campaign. This study is only focused on messages that has a length of 1 time slot. So here are the 7 types of messages that we received with the percentage. We can see that 95% of the received messages come from class A equipment. It's type 1, 3, and 24. About 4% comes from base station, type 4 and 11, and less than 1% comes from class B equipment type 18. So there's a majority of class A equipment as expected. Position reports that are messages of type 1, 3, or 18 for class B equipment are emitted periodically with a given repetition interval. We wanted to check if the observed repetition interval in this campaign was consistent with the theoretical repetition interval given by the ITU recommendation. So we computed the elapsed time between the beginning of two successive bursts from the same transmitters, and we plot over time this elapsed time. And for this first example, the theoretical repetition interval was of 10 seconds, but you can see that in practice it fluctuates between 8.5 and 11.5 seconds. In the second example, we have course changes for the chips. In this case, during the course changes, the repetition interval is supposed to decrease to about 3 seconds, and it's the case. You can see the decrease of the repetition interval. All observed transmitters had a repetition interval consistent with the ITU recommendations. Next point, the AIS channels. Transmitters are supposed to send messages on both channels alternatively. We wanted to check if this rule is well applied in practice. So we plot for a given transmitters the channel used over the time, and you can see the alternation. And in addition, the percentage of received messages on each channel is well close to 50%. Last point, the SOTDMA frames. The point is to know if the messages are well positioned in the SOTDMA frames. That means if there is a natural number of time slots between the beginning of each messages. So we compute the difference between the emission date of the messages, of the successive messages, and we plotted the decimal part of this difference. So for the majority of bursts, this decimal part is close to 0 or 1. That means that they are well positioned in the frame, that there are a natural number of time slots between them. But you can see that some bursts are shifted. Some bursts are as a shift equal to about 0.1 time slot. This burst has been sent by Class B equipment. Class B equipment listen to the channel before send their messages, so that explain the shift. But there's also a burst shifted of about 0.3 time slot. These bursts have all been sent by base station, and this behavior is by now unexplained. The last case is some bursts that have a shift of half a time slot. All these bursts have been emitted by Class A equipment, and this behavior is also unexplained. So to conclude, all treated acquisitions have shown a convergence in the analysis. There's no acquisition that has given completely different results from the others. And this measurement campaign helped us to improve signal processing algorithm and chip detection and identification algorithm. Thank you for your attention.
Any question? Just.
Okay, thanks. Do you track another access scheme than SOTDMA? Is there in that scenario some equipment like aids to navigation or repeater, or only class A ships?
We received only Class A and Class B equipment. I don't notice another type of equipment in the received signal.
You mentioned in your analysis that for a ship that should have emitted every 10 seconds, you have a jitter between 8.5 seconds and 11.5 seconds. Yeah. Have you made analysis on the statistic of this jitter? Is it uniform in minus plus 15% or 10% or Gaussian or?
No, we actually this fluctuation was expected because it's given in the IT recommendation. So we don't do a statistic study of its fluctuation.
Last question on the power profile during ramp up. Do you have some model on this power profile, like classical exponential increasing, or if you can please comment on?
The power ramp up is I don't remember well, but there's I think the 4 last bits are where the increase is the most important. The first bits are quasi impossible to decode because they are lost in the noise.
Okay, thank you very much.